My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar, and I'm happy to share you all with all that. Today it's our 90th International Physics webinar. Good evening to all here in Bangladesh, and a very good afternoon to all those who are watching this program live from UK. As we know that we are staying in a corona pandemic situation, we cannot continue our normal academic program inside the campus. So we have to start our online program. Our Department of Physics, Pabna, University of Science and Technology has started its online program. And we have already completed our 89th International Physics webinar. So we are trying to adjust with this new normal situation. So today is a very important day for our department. Today I'm going to welcome you all to a joint session between our Department of Physics, Pabna, University of Science and Technology, and the Department of Physics, King's College London, Cambridge, UK, in gravitational waves and high energy physics. And we have with us here today Dr. John Ellis, CB, FRS, Professor Clerk, Maxwell, Professor of Theoretical Physics, Department of Physics, King's College London, Cambridge, UK, and he has already connected with us. So I'd like to welcome our speaker. So, good afternoon, sir, and good evening here. So thanks for accepting our invitation. This is your second lecture in our series. So it's your time, sir. You can start. I think all of you have come to know that the title of our today's webinar is Gravitational Wave, and our speaker is Dr. John Ellis, sir, CBE, FRS, Professor Clerk, Maxwell, Professor of Theoretical Physics, Department of Physics, King's College London, Cambridge, UK. So he has already connected with us. So thanks, sir, for accepting our invitation. It's your time, sir. You can start your session.
Okay, well, thank you very much for the invitation to talk to you again. So this time I'm going to talk to you about gravitational waves. So we've been very lucky in the 21st century already to have had two really major discoveries. I talked a bit about the Higgs boson last time, and now I want to talk about another world-shaking discovery, that of gravitational waves. When I say world-shaking, I mean literally. As gravitational waves pass through the Earth, they cause its shape to change, like what you see here, changing from a cricket ball to a rugby ball and back again. During the passage of a gravitational wave of the type that's been observed, the Earth expands and contracts by, roughly speaking, the diameter of an atomic nucleus. So this is, of course, a big exaggeration of the effect, but it shows you the sort of effect that has been seen. So what I'm going to do is I'm going to review the gravitational wave story so far. Then I'll talk about the observations that have been made of black holes and neutron stars merging. I'm going to stress how important it's going to be in the future to cover the entire spectrum of gravitational waves, like it was in the case of electromagnetic waves. And I'll mention a couple of projects that I'm involved with to measure the spectrum in different regions of frequency. And I'll discuss the prospects for future observations of gravitational waves from mergers, from phase transitions in the early universe, and from cosmic strings. And one very exciting development in the last couple of months has been some observations by the NANOGrav experiment, which looks at the fluctuations in the timing of arrays of pulsars, and may possibly have found some evidence for cosmic strings. I'll return to that later. So, as you all know, general relativity was proposed by Einstein in 1915, and it was the following year that he predicted the existence of gravitational waves. And this is the paper where he discusses this prediction. And as you could see also from the poster, these gravitational waves are emitted when you've got two very massive objects rotating about each other and gradually falling in to merge. So all this is very well known. What's perhaps less well known is that in 1936, Albert Einstein drafted a paper where he tried to retract his prediction. The paper was sent to the journal sent it to a referee. Einstein was very upset because he said, "How dare you send my paper to a referee?" But the referee pointed out that Einstein's retraction of the gravitational wave prediction was in fact not correct, and the final version of Einstein's paper confirmed his prediction that gravitational waves should exist. So the first attempts at detection of gravitational waves came in the 1970s, when Joseph Weber, whom you see on the picture of the right, looked for vibrations set up in large metal bars. So he was using aluminium bars. They weren't very sensitive. Subsequently, there was an experiment at CERN using a cryogenic bar, but there again, they were orders of magnitude away from the necessary sensitivity to observe gravitational waves. The first detection was actually indirect, and it came about when Hulse and Taylor observed in 1974 a binary system containing a pair of pulsars. So here's an illustration of the pulsars rotating around their center of gravity. Pulsars, as you know, emit beams of light, a little bit like a lighthouse, and those are very precisely timed, and the emission of gravitational waves causes the orbits of the pulsars to change, and that alters the timing of the emissions from the pulsars. And on the left, you see a picture of how the pulsar timing changed over many years. And those measurements have given extremely precise tests of the theory of general relativity. As perfect agreement with Einstein's predictions, and Hulse and Taylor got the Nobel Prize in 1993. The bottom right picture, by the way, shows you the radio telescope where they made their observations. Okay, so that was indirect evidence for gravitational waves. In fact, we expect gravitational waves to be emitted over a very broad spectrum. So here you see frequencies ranging from 10 to the minus 16 to 10 to the plus 2. And these could originate from all sorts of possible sources. Quantum fluctuations in the very early universe, astrophysical sources. And this gives rise potentially to a new type of astronomy looking for different sources in different frequency ranges. So I'm going to be saying a little bit about astrophysical sources. In fact, the sources that have been definitely observed so far are astrophysical in nature, black holes and neutron stars. There are active programs to look for cosmological sources, for example, perturbations in the cosmic microwave background radiation that could be generated by quantum fluctuations in the early universe. There have been experiments, terrestrial experiments using interferometers, and arrays of pulsars. Their timing has been measured, and that's what maybe gives you a hint that there might be some other source of gravitational waves about to be discovered, as I'll discuss towards the end of my talk. So the direct discovery of gravitational waves started in 2016 with the measurement by the LIGO experiment in 2 separate locations of gravitational waves. So they have 2 locations in the United States. One is in the state of Washington in the northwest, and one is in the state of Louisiana in the south. And in each of those 2 locations, they put L-shaped detectors where the arms of the L are about 3 or 4 kilometers in length. And in those arm lengths, they set up laser beams. So what they then did was they looked for interference between the 2 laser beams, and those interference patterns change according to the expansion and contraction of space. So the idea here is that you have a laser at the bottom there. There is a beam splitter, so one part of the beam goes along the arm to the right, and the other one along the arm to the left. At the end of the arm, there is a mirror, which reflects the laser beam back. There is another mirror close to the source, which reflects the beam back again, so the beam goes backwards and forwards many, many times. What you eventually do is you look for the interference pattern between the 2 reflected beams, and you look for this pattern in a photodetector on the right-hand side. So that's the conceptual design. Here is another picture of it. So now you see the laser on the right-hand side. You see the beam splitter in green. You see the mirror at the bottom, a mirror on the left. The beams are reflected back. And in this picture that you see at the moment, the 2 beams, when they come back, are in phase and they reinforce each other. However, if a gravitational wave passes by, then maybe the path lengths in the 2 arms of the detector will be slightly different. And in that case, instead of reinforcing, the 2 beams may interfere negatively and cancel each other out. And that's what's illustrated in the right-hand picture here. So the LIGO experiment and its sister experiment, Virgo, have been under construction, commissioning, and operation for over 20 years now. So the picture here shows you some people installing part of the LIGO experiment, specifically some of the mirror system. And here is a close-up of part of that mirror system. As you can see, it's extremely advanced technology. One of the particular issues is that you have to suspend the mirrors in such a way that they're completely isolated from any shaking of the ground around them. So in Louisiana, they have to worry about alligators walking around, and in Washington, they have to worry about trucks. Okay, so here again is a picture of the LIGO layout. So as you can see, the arms are about 4 kilometers in length. The mirrors are what are called test mass in these 2 pictures. Over on the left-hand side, you see geographically where the 2 LIGO detectors are located. And the inset shows you the sensitivity that the 2 detectors reached in their first physics run. So they were looking for gravitational waves with frequencies, let's say, around 100 hertz. So their sensitivity range stops somewhere around 10, 20 hertz, and it goes up maybe to above 1,000, but the maximum sensitivity is about 100, 200 hertz. Just to remind you, the geometric change induced by the passage of a gravitational wave corresponds to changing the diameter of the Earth by something like the size of an atomic nucleus. So the so-called strain is very small in dimension. It's in units of hertz to the minus a half. It's around 10 to the minus 23. So what was observed? So here you see the signals from the first gravitational wave to be detected. In blue, we have the detector in the state of Washington. In orange, we have the detector in the state of Louisiana. And as you can see, there's no question something happened, and that something was very similar in the Washington and Louisiana detectors. So in the bottom panels, overlaid on the signal is the calculated effect of a gravitational wave from a merger of black holes with particular masses that I'll come back to in a moment. And you can see that the pattern is very similar to the data. So, perfect agreement with gravitational wave predictions. What you also see is that as you go from left to right, the frequency of the gravitational waves increases. And that's expected in the later stages of the merger when the two black holes fall into each other. So this is what one expects to see. So as I just commented, going from left to right, the frequency gradually increases. And that happens as you progress from the early stages of in-spiral through infall into the merger, where you get the maximum intensity of gravitational waves. And after the merger itself, you've got a blob there, which rings down until it eventually becomes a spherical black hole. So the bottom panel of this picture shows you how the separation between the two black holes evolves and how the relative velocity increases. So at the end there, you have relative velocities which are, let's say, a half the velocity of light. You have a separation which is very close to the Schwarzschild radius, RS. So this is a tremendous hadron collider. In my previous talk, I talk about a large hadron collider. This is way, way bigger. You're colliding much bigger objects. So as I commented earlier, the observation of these gravitational waves is a new way of studying the universe. And so now I want to discuss what we've learned. So this first event was due to the fusion of two massive black holes, and fitting those vibration curves, it was possible to estimate the masses of the two black holes in that first event were about 36 and about 29 solar masses, respectively. And the amount of energy released was incredible. The total radiated energy was something like 3 solar masses. So I commented that the frequency changed as a function of time. And that's what you see in these pictures here. So these are the signals observed in the two detectors. So on the horizontal axis, we have time. So this merger was observed for a fraction of a second. And during that time, the frequency went up from about 50 hertz to over 200 hertz, as you can see in these two pictures. So as I already commented, this is exactly what one expects as you have an in-spiral of two black holes, the separation decreases, the orbital period decreases, and the frequency increases. So the fact that you're able to observe gravitational waves over a range of frequencies tells you that the mass of the graviton is less than about 10 to the minus 27 times the mass of the electron. If you had a non-zero graviton mass, it would affect low-frequency gravitational waves more than high-frequency gravitational waves, and the chirp structure would be changed. So in general, there are modifications of relativity in which waves of different frequencies travel at different speeds, but what these data tell you is that waves of different frequencies seem to travel all at the same speed. So that was the first event. Here I show you the mergers that were measured in the first observation period of LIGO and its sister detector, Virgo. So you can see the characteristic chirp pattern, which is more or less visible in all these insets. I draw your attention particularly to this bottom right-hand panel. So here you see a clear chirp signal extending over tens of seconds, something like 100 seconds. This is a different type of merger from the black hole merger that we were talking about before. In fact, it is a merger of a pair of binary neutron stars. So when LIGO and Virgo made this observation, they immediately shared the information with electromagnetic detectors around the planet, and some of the detectors looking for X-rays saw a signal which is almost coincident with the gravitational wave signal from the merger. So in this plot here, I show you the light curve from the Fermi satellite and from the integral satellite, which observe in various different frequency ranges. And in both cases, you see a peak that occurred about the order of a second after the gravitational wave event. So that is understood because we would expect that if you have two neutron stars merging, the optical flash would occur a little bit later than the arrival of the gravitational waves. Now, obviously, by comparing the arrival time of the optical radiation and the gravitational waves, you can compare the velocity of light with the velocity of gravity, and the two are very similar to 1 part in something like 10 to the 15 or so. In addition to the Fermi and integral satellites, many other telescopes looked for and saw light coming from the same direction as the LIGO-Virgo gravitational waves. So a paper was produced involving LIGO, Virgo, and something like 70 astronomical teams with observations of the optical radiation over a tremendous range of frequencies. And all this is what you'd expect from a neutron star merger, which produces large amounts of radioactive isotopes, which then produce energy, electromagnetic energy, which you can detect. So this is a wonderful confirmation of the theory of such events. So this is a summary of the current status. So now, in the first two runs of LIGO-Virgo and the first part of the third run, they have observed a total of 50 events. And this picture here shows you the masses of the objects merging and the mass of the object formed by the merger. So what you see in blue are the mergers of black holes. Down the bottom, you see a couple of mergers of orange things, which are like the neutron star merger, which I showed you on the previous slides. So they have a couple of such events, one of them which was very spectacular, I just told you about, and another one where they didn't see the optical counterpart. What you also see, if you look carefully, is a couple of events which look like the mergers of objects of very different masses. So there's one of a merger between something where less than 2 solar masses and not something more than 5, and something of the order of 3 solar masses with something above 20. So the interpretation of those events is still not clear. What you also see in purple is the masses of black holes that have been identified purely on the basis of electromagnetic radiation, no gravitational waves, and in yellow, the masses of neutron stars that have been measured accurately. So I'd like to draw your attention also to this event at the top. So this is the most massive merger that's been seen so far. So you have 2 black holes, one with a mass of about 60 solar masses and one with a mass of above 80, which merged to form a so-called intermediate mass black hole weighing 150 or 160 solar masses. So this is the signal that they observed. So in this case, you don't really see a chirp. What you see is more of a sort of bang coming from the last stages of infall, the merger itself, and then the final ring down. Interestingly, in this case also, they saw an optical counterpart, well, I should say a possible optical counterpart, which didn't appear immediately. As you can see from the scale at the bottom, it occurred something like a couple of months later. And there's a theory for how this could have arisen if the merger took place within some accretion disk around an active galactic nucleus. Okay, so that's where we are at the moment. What next? So there are 2 more large gravitational wave experiments which are in progress. One is a so-called Kagra experiment in Japan, which differs from LIGO-Virgo in that it's cryogenic, it's not quite as big, and they just started taking data in collaboration with LIGO and Virgo. Also planned is a detector in India, which basically uses clones of LIGO components to build a third LIGO-like detector in India. I might mention also, you can see up the top there, a detector called GEO, which has been operating for some time, but it's quite a bit smaller than LIGO and Virgo and doesn't have the sensitivity to see the sorts of gravitational waves that I've been talking about. So what is the future? So there is one project which has been approved by the European Space Agency in collaboration with NASA, which is to put a laser interferometer in space. And here is an illustration of it. It would be located away from Earth at one of the stationary orbitary points. And another project for a laser interferometer in space is being proposed in China. So what would be the sensitivity of such a detector? So in this picture here, over on the right-hand side, you see the frequency range to which LIGO and advanced LIGO are sensitive. So they're ideal for observing compact binary inspirals, and they might also be able to look for supernova. Then in the middle of the picture, you have LISA. So LISA is optimized for a frequency of 10 to the minus 2 hertz, so 4 orders of magnitude away from the maximum LIGO sensitivity. So what could you observe there? Well, you could observe massive binaries, for example, involving supermassive black holes, or mergers where you have one very heavy object, one much lighter object, say a sort of solar mass black hole falling into a supermassive black hole. So just to remind you, many, if not most, nuclei contain supermassive black holes in their middle. As you will perhaps remember, a while back, the Event Horizon Telescope observed or gave an image of one of these supermassive black holes, which is located in the M87 galaxy. And this black hole has a mass of 6.5 billion solar masses. There are others which are bigger. The black hole in the center of our own galaxy is relatively small. It has a mass of a few million solar masses. Okay, so let's look again at the gravitational wave spectrum. So over here on the left, in cyan, you've got the sensitivity of cosmic microwave background radiations. Over on the right, you've got LIGO, with, as I said, a characteristic frequency of the order of 100 hertz. Then in red, you've got LISA, optimized around 10 to the minus 2, 10 to the minus 3 hertz. Also shown in green is pulsar limit. So that's a limit coming from observations of arrays of pulsars. I'll come back to that later on. That has an optimal sensitivity about 10 to the minus 8 hertz. So we immediately see that there are some gaps in our coverage of the spectrum. For example, there's a gap between the optical interferometers on Earth and LISA. And as I'll discuss now, that could be an interesting window to explore to see the formation of supermassive black holes and possible effects in the early universe, such as electroweak phase transition or cosmic strings. There is, of course, another gap between LISA and pulsar timing arrays, but I'm not going to discuss that here. I'm going to focus on this so-called mid-frequency band around 1 hertz. So I'm involved in a collaboration in the UK called AON, which has just secured initial funding. And what we plan to do is to build a series of detectors based on the principle of atom interferometry. So here the idea is that instead of interfering laser light beams, you interfere cold atoms. You hit an atom with a laser, which then excites it, and it causes the atom to move, and you look for interference patterns between the atomic de Broglie waves. These interference patterns are sensitive to the modulation of the light travel time caused by a passing gravitational wave. So, as I mentioned, this is a staged program. We're going to start off by constructing small devices, hoping to lead up to construction of a 10-meter interferometry device. Following that, we would hope to scale up to a 100-meter device, which would have interesting astrophysical and cosmological capabilities, as I'll show you a bit later. Eventually, we would hope to build a terrestrial device of 1 kilometer in length. And our big dream is to construct a space-based version, so an atom interferometer in space, paralleling, in some sense, the laser interferometer. So this is the title page from the paper that we wrote about this space-based proposal. We submitted it to the European Space Agency as a possible project to be considered around the year 2050. And we're now looking forward to hearing what ESA has to say. So what could you do with these atom interferometers operating in the mid-frequency band? So one topic is astrophysics. So I talked earlier on about those supermassive black holes in the centers of galaxies. How do you make an object weighing maybe 10 to the 9 solar masses? So there's various different ideas about how this might have happened. Maybe you assemble the first generation of so-called population 3 stars, or maybe they collapse into black holes, and you put together a supermassive black hole as if those stellar black holes were Lego bricks. Or maybe you put together proto-galaxies, each of which has a black hole with a mass maybe of 100,000 solar masses. So there's various different ideas of how you would assemble those supermassive black holes. But typically, they would involve mergers of black holes with masses intermediate between what's been observed by LIGO Virgo and the supermassive black holes in the cores of galaxies. So this picture illustrates the sensitivities of various different gravitational wave detectors as a function of frequency. So over on the right-hand side, we've got LIGO and a possible follow-on detector called the Einstein telescope. Over on the left, we've got LISA, optimized around 10 to the minus 2 hertz. There's a gap in the middle, and that's where these atom interferometer experiments, AON and EDGE, would come into play. Now, the lines there show you the evolution of the strain coming from different types of mergers. So LIGO, sensitive to mergers of 60 solar mass objects, as you've seen. LISA will be sensitive to mergers of objects weighing 1 million solar masses. Intermediate black holes with a mass of maybe 10 to the 4 solar masses, the best way to look for them would be in the mid-frequency band, which is covered by AON and EDGE. And as you can see here, you can hope to measure such mergers out to redshifts of the order of 5 or so. So in this way, you can probe the formation of supermassive black holes. And I might comment that there's plenty of synergies with other gravitational wave experiments. For example, LIGO might tell us that a merger of a 10 to the 4 solar mass black holes is coming, but you would observe it with AON or EDGE. Or AON or EDGE could tell you that there will be a merger of 260 solar mass black holes, and LIGO or ET could observe it. So what could you do with the measurements of such black holes? Well, one thing you can do is you can constrain the graviton mass. I already mentioned this. The first limit provided by LIGO and Virgo. Their current data set give you a limit of about 1.8 times 10 to the minus 23 electron volts. So what could you do with with AON or EDGE? Well, if there was another LIGO or Virgo event, which surely there will be, you could observe it over a much longer time, maybe 10 days, maybe 100 days, and you could predict exactly when it's going to occur. You could also potentially observe mergers of heavier black holes, as I just discussed. Longer observations give you more precision. Lower frequencies give you, heavier black holes give you sensitivity to lower frequencies, which give you greater sensitivity to the graviton mass. So we looked at this, and with AON, you could hope to measure an upper limit of the order of 10 to the minus 24 electron volts, so an order of magnitude better than LIGO Virgo. Another order of magnitude maybe with heavier black holes, and EDGE would be even an order of magnitude better, going down below 10 to the minus 26 electron volts. So this would be a fantastically precise test of general relativity. How about looking for possible extensions of the standard model of particle physics? So in this picture here, I show you a simulation by David Weir of phase transition, a first order phase transition in the early universe. Now, in such a phase transition, you nucleate bubbles of the new true vacuum, which sit in a background of the old false vacuum. Then, as time goes on, those bubbles expand, and if you're lucky, eventually they fill all the space, a process called percolation. So you have this percolation of bubbles of the new vacuum. As the new vacuum bubbles grow, they collide, and you can generate gravitational waves either in the collisions of those bubbles or in the turbulent plasma which is formed after the collisions. So we've been looking at the generation of gravitational waves in such a first order phase transition in a couple of particle physics models, which are of interest because this is also the sort of particle physics that you can look at in colliders, either the LHC, which I mentioned in my previous talk, or some future collider. So here, for example, is the signal that you would get if you added to the standard model a sixth order interaction between the Higgs bosons. So here I show you the strongest signal where you can be sure that the phase transition will be completed And you see that both edge and laser would be sensitive. In fact, their sensitivities are very similar. Alternatively, you could consider a model in which you have an additional gauge boson associated with an additional U1 symmetry. So this model has more degrees of freedom. You can characterize it by the temperature to which the universe reheats after the transition has taken place. And depending on whether the transition takes place at 100 GeV or 10 TeV or 1000 TeV, you would get best sensitivity in laser or in the mid-frequency Aon edge band or in the high-frequency LIGO ET band. So now I want to talk about another possible source of gravitational waves in the early universe, namely cosmic strings. And I want to mention a possible hint for cosmic strings that has been found recently by the NANOGrav experiment looking at the timing of an array of pulsars. So cosmic strings are represented by these lines here. Those strings can meet each other and they can form loops, and those loops radiate gravitational waves. And this is a simulation by the Cambridge Cosmology Group of what a network of cosmic strings might look like. So the yellow wiggly lines are long pieces of string, and the little red things, those are loops of string, which are the most important sources of gravitational waves. So one of the interesting characteristics of these stringy gravitational waves is that they have an extended range of frequencies. In fact, it extends, basically gives you a flat spectrum over many, many orders of magnitude. The height of the spectrum depends on the tension of the strings, and that's characterized by Newton's constant G and an energy parameter related to the string called mu. And here we've got curves corresponding to different values of mu, and you can see that the maximum value of mu that's allowed by the pulsar timing arrays over on the left-hand side is somewhere around 10 to the minus 11. So the spectrum is almost flat, but not quite, and that means that LIGO is perhaps a bit less sensitive than the other detectors. Okay, so I've talked about pulsars and I've talked about so-called pulsar timing arrays. So what are they exactly? So here I've illustrated in black some pulsars. So as you know, they can emit beams of radiation, electromagnetic radiation, which move around in the sky much like lighthouse beams. Now, the timing of the pulsars and the motion of the beams is affected by the passage of a gravitational wave. So there's several groups looking at these pulsar timing arrays, and a couple of months ago there was a very interesting paper by the NANOGrav collaboration. So they've been observing pulsars for 12.5 years, and this is what they observe. So on the left-hand side there, you see 12 to the far left, you see what looks like a significant signal, which is not purely noise. So in the right-hand half of the left panel, there's noise, but over in the left part, it looks like there's something sitting above noise. And the NANOGrav collaboration reports in their paper, quote unquote, strong evidence for a stochastic common spectrum process at frequencies below 10 to the minus 8 Hertz. So that's exactly what you could get from cosmic strings. It's also possible that you could get it from the mergers of supermassive black holes. So in the right-hand side here, I show you fits from the NANOGrav paper to the amplitude of the signal as a function of the spectral index, gamma. So the preferred magnitude is something like an amplitude of 10 to the minus 15, and with a characteristic slope parameter, which is about 5. Now, also shown in this picture is a vertical dashed line, which is what one would expect naively from a model of mergers of supermassive black holes. So this model of mergers of supermassive black holes is somehow the sort of default model. If you asked an astrophysicist, they would say, oh yeah, this must be due to black hole mergers. However, as you can see, it's not a perfect fit to the data, and that encouraged us to think about a possible cosmic string interpretation. So here I show you a line in sort of rainbow colors, which is the cosmic string prediction as a function of the cosmic string tension in the range 10 to the minus 11 to 10 to the minus 9. I also repeat the vertical line, which is the naive supermassive black hole merger prediction, and upper limits from previous pulsar timing array experiments. So you see there's one upper limit there from NANOGrav, which is consistent with what they're reporting now, although the new data have a better analysis and they tell you, well, you shouldn't pay attention to the old NANOGrav data. So this is zooming out on the spectrum that you might get from cosmic strings. And so the interesting range is somewhere between 10 to the minus 10 and 10 to the minus 11. This is, as I said, it's compatible with the NANOGrav measurements. It's compatible with the European pulsar timing array at the bottom. There is one other pulsar timing array called the Parkes pulsar timing array, which is shown there in green. So they're probably the ones that exert the most pressure on this interpretation of the NANOGrav data. Okay, so that brings me to the end of what I wanted to say. So in summary, our experience with electromagnetic waves shows the advantages of making observations over a whole range of frequencies, and we expect the same to be true for gravitational waves. So there are experiments in various different frequency bands. AON and its successor EDGE offer a program for exploring gravitational waves in the mid-frequency band using atom interferometry, and there you're sensitive to intermediate mass black holes, first-order phase transitions, and many other astrophysical and cosmological sources. EDGE would be a natural continuation of the AON program, putting an atom interferometer in space. So as I mentioned, one very exciting recent development is the possibility of gravitational waves having been observed by the NANOGrav pulsar timing array. And if that observation is confirmed, maybe it comes from cosmic strings. So I should mention that atom interferometers are also useful for exploring the nature of dark matter, in particular ultralight dark matter candidates, and there are other possible opportunities in fundamental physics, astrophysics, and cosmology, which we're still exploring. So I hope I've convinced you that this is an area of interdisciplinary science, which is unique in giving us insights into astrophysics, cosmology, as well as fundamental physics. And I finish with this slide here. So one bird says to the other, was that you I heard chirping just now, or was it two black holes colliding? So, thank you very much.
Thank you, sir, for your wonderful session, sir. If you allow, sir, we can start our discussion session, sir. I can add the question in the screen so that you can also see the question. So, the first question, what is the full form of Kagar and LIGO?
Okay, so the first question is, which is the nearest black hole to Earth, and can it consume the Earth? So I think we don't know what is the nearest black hole. The nearest black holes that I'm aware of are thousands of light years away. There's probably others, maybe hundreds of light years away, but there's no way that they could consume the Earth, because in order to do that, they would have to accumulate enormous amounts of material, which is just not present in interstellar space. So no need to worry about getting eaten by a black hole. Next question. What's in the interior of a black hole? To be honest, I don't think that we know. There's all sorts of conjectures about what may be going on in the interior of a black hole. In particular, some of you may have seen the movie Interstellar, in which there's a lot of good science explaining, for example, how time slows down in a strong gravitational field. But there's also speculations about what happens inside a black hole and about time travel, which I think are just pure bullshit. Okay, so those are the two questions that I see in the chat window. Now, the question which I see
I have
in the main window
in the screen
from Bidjut. What is the full form of Kagra and LIGO? So LIGO, that's easy. That's I think it's, I'm not sure whether it's large or Livingston. No, it's Laser Interferometry Gravitational Observatory. Okay, Laser Interferometer Gravitational Observatory. Kagra, that actually has an A at the end, and I'm afraid I don't know all of what it stands for. The Ka, I think, comes from Kamiokande, which is the location. It's located close to the Kamiokande neutrino detector. Gr, I can imagine, is gravity. But as I said, there's also an A at the end, but I don't know what that might be. Perhaps just GRA is just gravity. Maybe it's just Kamioka gravity. I don't know. Sorry. Any more questions?
Yeah.
Does gravitational waves decay?
Does gravitational waves
Thank you for
decay?
the question, Yusuf. No. Gravitational waves just propagate in the same way that electromagnetic wave does not decay. Of course, as they travel, they spread out. So it's a little bit like ripples in the surface of a pond. You put in a stone, you get a big ripple, and then as you go further away, the ripple gets smaller and smaller. So it decays in the sense that the amplitude gets smaller, but there's no dissipative process.
And there is another question. How these strings are
How
directed.
these strings are directed. So, Sheikh, these strings are basically random. So the picture that people have in mind for the origin of these strings is that there is some order parameter, maybe the expectation value of some Higgs-like field. And this order parameter maybe has different directions in different parts of space. So you could imagine a sort of hedgehog configuration where it points in different directions around some sort of circle like this. And then, of course, if it's pointing in different directions, what happens in the middle? So in the middle, there's what we call a defect. And a string is an example of a one-dimensional defect. Okay. Now, where this string is located in our physical space is completely random. And you saw that in the simulation, that the strings were kind of pointing in all sorts of different directions.
We have another question, sir.
Can you tell us about the most recent observational results on the Maxwell mass of neutron stars? So we know now of various neutron stars which weigh a little bit more than twice the solar mass. But there is at least one example, I showed you, pointed it out to you in a slide which was showing the stellar graveyard, where there was a merger involving an object which was significantly more than 2 solar masses and significantly less than 5 solar masses. 5 solar masses is thought to be the minimum for a black hole. So people don't know what that object is. Is it somehow some small black hole which escaped the limits that we thought we'd established? Or is it a very heavy neutron star? Or is it maybe some other sort of object, maybe a quark star, or some other sort of exotic compact object? So I think at the moment we don't really know. And I think we're waiting for more observations to tell us whether there are more objects like that and get some better picture of what's going on.
Thank you, sir. We have another question, sir. Sir, can we use
gravitational waves in our practical life? If yes, then how? Well, okay. There's an old saying that if some old physicist tells you that something is impossible, don't believe them. So I'm nevertheless going to say I can't imagine how we can actually use gravitational waves. But maybe somebody very clever is going to come up with some way of doing it. But I'm afraid I don't know what it is. I should say that there are other aspects of general relativity which are useful in our everyday life. So, for example, the global positioning system which connects to your phone so that you know where you are, in order to interpret, so that uses signals from atomic clocks in satellites. In order to interpret those signals, you need to incorporate the effects of special relativity from the satellites moving around, but also the effects of general relativity, because those satellites are at a non-trivial altitude, and you've got a gravitational redshift which comes in between different altitudes. So general relativity is already playing a role in our mobile phones, and but maybe not gravitational waves.
Thank you, sir. So, free energy theory. Maybe what is
free energy theory? With 4 exclamation marks. So, George, I'm not sure whether that's a question, and if it is a question, what the question is. Maybe you could describe your question in a bit more detail.
Sir, so you have another question. This may be the last question, sir. Okay.
Please analyze cosmic microwave background and the relationship between dark energy. Can we collect this energy? Is there any way we can use this energy in the near future? So the cosmic microwave background radiation was, of course, emitted when the universe was about 380,000 years old. And it was emitted when light in the universe decoupled from atoms. Now, that light, which we now see as microwave radiation, exhibits small variations in spatial direction. It has different intensities. And we think that that is due to fluctuations in some sort of field, maybe a little bit like the Higgs field, maybe even the Higgs field in the very early universe. Now, those fluctuations, as observed by the cosmic microwave background radiation, tell us something about the content of the universe, how much matter there is, and how much energy there is. And it was a combination of those measurements, together with other measurements, more traditional astrophysical measurements, that tell us that something like 2/3 of the energy density of the universe is in the form of an energy density spread throughout empty space. So this, as far as we can tell, is uniform, homogeneous, isotropic, omnipresent, entirely featureless as far as we can see. Now, we don't know of any way to extract this energy. It's possible that this energy is somehow associated with a field. Maybe this energy is very slowly changing, and as this change takes place, there's maybe some field involved which we could maybe use for some purpose. But if we can, I think that's a long way off.
Thank you, sir. As there is no more question, we should conclude our discussion, sir. Thanks for your nice presentation and wonderful discussion session, sir. We would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir, for accepting our invitation. You have given 2 lectures for our student. We are very grateful to you, sir. So thanks for everything, sir. So it was a very great webinar with you, sir.
Well, thanks again for the invitation, and
it's my honor and privilege, sir, to host you in our International Physics Webinar. So bye today, sir. Goodbye, sir. Good night, sir.